Okay, this video is on section 14.8, which is about Lagrange multiplier. And I'm going to cover everything in this section in one video. And this is the last video for section, not section actually, for chapter 14. Anyhow, let me start with an example. So here's an example. Find the extreme value either maximum. Extreme value means either maximum or minimum. If it exists. Of z is equal to x squared plus y squared. Then now, okay, first of all, we have seen this function before. Z is equal to x squared plus y squared, and that's rotated parabola, which is called a paraboloid. Right? If we just ignore y, it's parabola, and if we just ignore x, that's parabola on the yz plane. And then it's actually three-dimensional parabola called the paraboloid. And indeed, a three-dimensional picture of this function looks like the following. All right, so this is a z is equal to x squared plus y squared. And here's a picture. It looks like this is like a parabola. If you look it on the xy plane, yz plane, or xz plane, it's parabola, but it's rotated parabola. Okay, so this function apparently takes the minimum value at the bottom. And then since this goes up forever, there is no maximum value. So this takes minimum at 0, 0. That's fine. However, the question we consider in this section is not that, but let me just go back to it. Here. So z is equal to x squared plus y squared. This takes minimum at 0, 0, and the minimum value is 0, and it doesn't have any maximum. That's fine. But here's a question we consider here. We want to find the extreme value, namely either maximum, minimum, subject to the constraint xy is equal to 1. Okay, we impose this condition on the x value and y value. So for example, x0, y0 gives you the minimum, but if x equal x0, y0, then the product is 0. So this equation is not satisfied. This constraint is not satisfied. So that doesn't give you the extreme value subject to this constraint. And then to find extreme value is a maximum minimum subject to a constraint like this is called the method of Lagrange multiplier. And that's what we're going to do in this section. But then now, let's think about this problem in the following way. So let's look at everything on the xy plane. So let's look at everything from the above. So z-axis appears as the dot, as the origin. Then remember level curves. So that means we have this, and as you increase the z value, you get the bigger and bigger circle. That's the level curve. So if you look at each level curve, at each z value, you get bigger and bigger circle, as we have seen in the picture before. Okay, then now we want to find the value, extreme value of the z, this z function x squared plus y squared, subject to xy is equal to 1. But what is this geometrically? Well, this is hyperbola, which looks like this. Like this. Okay, so that means z value subject to constraint corresponds to those points here that intersect the level curve with the hyperbola. So this is xy is equal to 1. And then now, from this, you could tell that the smallest z value, that's essentially the smallest radius, that intersects with xy equal to 1, namely that intersects with this hyperbola, appears here, namely the point where, the point where the level curve just touches the hyperbola. And those two points give you the extreme values. So those are extreme values. But then now, geometrically, at the point where you get the extreme value, what's happening? Well, remember, if you compute the gradient, well, let me just say before that, let me just say, sorry. Let me just write down what I just said. So to find the extreme value subject to constraint is actually essentially the same as to find the value, the z value of z is equal to x squared plus y squared when at that point x and y are on the curve xy is equal to 1. All right. Then now let me just put f of xy as x squared plus y squared and g of xy as x1, namely the left-hand side of the constraint function. Okay, then, like I said, at extreme points, so to speak, extreme value, extreme points, those two curves touch with each other. But what does that mean? Well, that means, remember, if you compute the gradient of the function, what you get is a vector perpendicular to the level curve. Remember, if you have a function like z is equal to whatever, then excuse me, if you compute the gradient is always perpendicular to the level curve. So that means if you look at the level curve, if you look at the gradient of f and the gradient of g, you get situation like this. Maybe here. Okay. So that means at the extreme points, gradient of f and the gradient of g are parallel. But what does that mean? That means more algebraically, gradient of f of x is proportional to the gradient of for some scalar. And you may assume that the scalar is zero, is non-zero, sorry. If scalar is zero, gradient is zero, but you may assume that the gradient is never zero for this type of problem. So this means as a vector, the gradient is written like this. And then on the right-hand side, the gradient is also written like this. Okay, and that is the same as saying is equal to lambda gx and lambda gy. So therefore, this is the same as saying f sub x is lambda g of x and f sub y is equal to lambda g of y. Okay, and then for this particular example here, this is computed as 2x is equal to lambda times y, and then 2y is equal to lambda times x. And then we also have this g of xy is equal to x. So that means xy, that's g of xy, is equal to 1. Then now, here, so that means we have those 3 equations with 3 variables. So in principle, you could solve these system equations. And the solution for the system equations gives you the extreme value. And the last equation, by the way, is, like I said, coming from the constraint. So all we have to do is just solve this system. Solve this system of equations. Now, like how? Then now, for Lagrange multiplier, so basically what you have to do first is set up these system equations and then solve the system. And the difficult part is actually to solve the system. And then it's almost always ad hoc. So you have to come up with nice way of solving system for each case. And then for this one way to solve this system is like this. So from equation number 1, you can solve it for y. And then you get 2x over lambda. And then you plug this into 2. So here, plug into 2. And then you get 2 times 2x over lambda. And that is equal to x lambda, lambda x. And that is equal to 4x is equal to lambda squared x. Then now, you may assume that x is not 0. And indeed, since we always have xy is equal to 1, x cannot be 0. So from this, 4 is equal to lambda squared. So this is because x is never 0. And then from this, you'll see that lambda is plus or minus 2. Okay, then once you get the lambda, now we are getting very close to be done. So first of all, lambda is equal to 2. What would happen? Well, if lambda is equal to 2, by looking at the first 2 equations, 1 and 2, we get 2x is equal to 2y, and then 2y is equal to 2x. But those are the same equations after all. But those are the same. And then from this, you get x is equal to y. And then since it's x equal to y, you get x squared equal to, so x is equal to y. Then now, once we got this, we use the constraint. By 3, we get x squared is equal to 1. So this is by 3. Okay. And then from this, you get x is equal to plus minus 1. And then if x is equal to plus or minus 1, since x is equal to y, that's also plus minus. Y is plus minus 1. Okay. Yes. So that's so therefore, as one of the solutions, we got xy is equal to 1, 1, and negative 1, negative 1. Okay. Now, how about lambda is equal to negative 2? Lambda is equal to negative 2. Once again, just as before, equation 1 and 2 gives you here negative 2. 2x is equal to negative 2y. And then this gives you x is equal to negative y, And then now by using constraint, you get negative x squared is equal to 1. Okay, but that means no solution. Okay. Of course, we are working with only real numbers, so no solution. This is by 3. So lambda equal to negative 3 doesn't give you any solution. So therefore, the answer is just this. The answer is the extreme values happen at those 2 points. Therefore, extreme values happen at 1, 1, and negative 1, negative 1. And their values, namely the corresponding z values, they are f of 1, 1. F of 1, 1 is, remember, f of xy is x squared plus y squared. So 1 squared plus 1 squared, that's 2. And f of negative 1 is negative 1 squared plus negative 1, 2. Okay. Indeed, geometrically, what we got is the picture I wrote at the beginning. So extreme values happen just when the level curve touches the constraint for the curve for the constraint. So the level curve is a circle, and then oops. The function we are looking at is z is equal to x squared plus y squared. So the radius, so z value is 2, meaning that the radius is root 2. So it's root 2 and root 2. When the circle just touches xy is equal to 1, radius is root 2, and the touching point is here 1, 1, and here negative 1, negative 1. Okay, so that's what's happening. So let me just summarize this method called the method of Lagrange multiplier. So in general, given z is equal to f of xy with constraint g of xy is equal to k. K is some fixed number. Then the z value takes extreme values when the level curve of the function just touches the curve given by the constraint. Given by the constraint, or given by this. Okay, and then more algebraic way of saying this is that two gradients are parallel. And this happens if and only if the gradient of f is a scalar multiple of the gradient of the other one for some scalar. And you may always assume this is non-zero. And more concretely, this is the same as saying f sub x, f sub y is equal to lambda g sub x, g sub y. And then that's the same as, more concretely, that's the same as f sub x is lambda g sub x, f sub y is lambda g sub y. And then g of xy is equal to k. So this is just a constraint. Then you get this system of three equations with three variables, x, y, lambda. And then what you have to do is just solve this system. Then solve it. System. And then this method is called the Lagrange multiplier. This method is called the method of the Lagrange multiplier. And strictly speaking, this number lambda, this scalar lambda is called Lagrange multiplier. And the method is called the method of Lagrange multiplier. But sometimes people just casually call the method the Lagrange multiplier. Anyhow, so if you didn't really understand this logic for the method of Lagrange multiplier, usually the problem is given like, given a function, find extreme values subject to the constraint by using the method of Lagrange multipliers. And if you see such problem, what you have to do is just set up this. Okay, and that's the same as setting up this, and that's the same as setting up this, and then just solve the system. But the difficulty is to solve this system. So this part is computationally the hardest part actually, but the method is just this. All right. Then now we can actually generalize this to functions with three variables. So let me work out such problem. Furthermore, this can be generalized. This means the method of Lagrange multiplier. This can be generalized. A function of the form w is equal to f of xy, or f of xyz subject to the constraint. To the constraint g of xyz is equal to k. And for this case, again, idea is the same. The gradients are equal. Lambda gradient g. The gradients are not equal. So gradients are proportional. And then you have the constraint. And then you get the system of equations. But in this case, system of equations, a system of 4 equations, because it has 3 variables. So therefore, f sub x is lambda g sub x. F sub y is lambda g sub y. F sub z is equal to lambda g sub z. And then we have the constraint. And that's k. And they get system 4 equations with 4 variables, x, y, z, and lambda. And k is just always a fixed number, so k is not a variable, just a number. And then what you have to do is solve this system. And of course, the difficulty is solving a system like this. And let me work out an example, typical example. A rectangular box is to be made. Oops. What happened? Rectangular box without the lid, without the cap, without the top portion, is to be made from 12 square meters of cardboard. So this is the total amount of material you are allowed to use. Cardboard. Then now, you want to optimize the volume. You want to maximize the volume. Find the maximum volume of this box. Oops, this box. Okay, how are you gonna do this? So here's the answer. Let me write down a picture. So you wanna make a box without a lid. Rectangular box, it looks like this. Like this. And let's call this side x, and this y, and this is z, height z. So volume is, of course, xyz. Volume. So this is the function you want to optimize. And this is x times y times z. And then you want to, so what you want to do is to maximize this. So we want to maximize this volume subject to the constraint what? Well, the total area of the cardboard you are allowed to use is 12 square meters. So that means what? If you open this up, you get something like this. This is x, and this is y, and then height is z, so z is here. Okay, just open up the box, you get this. Now, the total area here has to be always this much, 12 square meters. So what's that? Well, the total area here is what? Well, you can actually compute it as 2xy, 2xz, sorry, 2xz. So that's this part. And you have two of them, that's why you have two. And then this part has the area yz, and then you have two of them here and here. So 2yz. And then the base is here, and the area is a xy, x times y, and you have only one of them, xy. And then this has to be equal to 12. So this is the question you have to solve. Namely, let f of xy, f of xyz, this is a function you want to optimize, you want to maximize, that's xyz. And then subject to the constraint function is this 2xz plus 2yz plus xy. And then this has to be always equal to 12. Okay, then now let's use Lagrange multiplier. Lagrange multiplier. Namely, we need to find xyz and lambda such that this two gradients are proportional, and the constant of proportionality is lambda. All right, and now this can be computed as what? Well, just like this, right? So if you compute the gradient of f, you get yz for the x component and xz for the y component and xy for the z component. And then this is equal to lambda times. Now you want to compute the gradient of this. You will see that this is 2z plus y, 2z plus x, and then finally 2x plus 2y. All right. Then now you can break this up into three pieces. This is equal to lambda times by extracting all the components, and xz is equal to this lambda 2z plus x, and then finally this is equal to this times lambda, of course. So that is xy is equal to lambda 2x plus 2y. All right. And then finally, we need to add the constraint to our system, 2yz plus xy is equal to 12. Okay, so we have this number 1, this number 2, this number 3, and this number 4. Now, so we have set up the system equations, and the difficult part is to solve this. And in this case, the equations are almost symmetric between x, y, z. Well, indeed, it's symmetric for x and y, but not for z, but it's almost symmetric. And therefore, one way to solve this is this. Let's multiply x to the first equation, and you get the xyz is equal to lambda times 2xz plus xy. Okay, and then this way you get the xyz, and you can similarly get xyz by multiplying y here. From this you get xyz, and this is equal to lambda 2yz plus xy. And then finally, from 3, you multiply z, you get a lambda and 2xz plus 2yz. And then let's call this number 1. Then, since we have the same thing here, we can equate those, so to speak. And then you get lambda lambda 2yz plus xy. Then now, we know that lambda is non-zero. So this is always the case. You may assume that for this type problem, you may always assume lambda is non-zero. And then therefore you get 2xz plus xy by dividing both sides by lambda xy. And then this is equal to 2xz is equal to 2yz. Okay, now we got this. But of course, z cannot be 0, right? Because z is a length. So you may assume that z is not 0. And so therefore, by also you may divide both sides by 2. You get this. So z is not 0. So x is equal to y. Then now, similarly, you can equate those because they have the same left-hand sides. So 2 prime is equal to 3 prime. And that is equal to lambda 2yz plus xy is equal to lambda 2xz plus 2yz. Okay, then once again, lambda is not 0. So you can divide both sides by lambda. Then now you can cancel 2yz from both sides. Right, and then you get xy is equal to 2xz. And then now we already know that x is equal to y. Okay, we already know x is equal to y. So therefore, this is written as x squared is equal to 2xz by x is equal to y. So I just plugged in y to x. And then by dividing both sides by x, you get 2z. Okay, because x is not 0. Okay. All right. So therefore, what do we get so far? We get x is equal to y. And then now, at the same time, x, which is the same as y, is equal to 2z. So x is equal to y is equal to 2z. Then now, let's use the constraint. So this, by the way, this happens even in the previous problem. For the method of Lagrange multiplier, usually you use the constraint at the very end. So let's use the constraint number 4, which is this. Let me just copy it. Constraint was 2xz plus 2yz plus xy is equal to 12. So that was the constraint. All right. And then just plug in those to the constraint. Now what do you get? Well, and express everything by z. So that means 2 times x is 2z times z plus 2 times y, but y is 2z times z, and plus xy, but xy is 2z. Both of them are 2z. That's equal to 12. And if you simplify this, you get 12z squared is equal to 12. And that is equal to z squared is equal to 1. And of course, z is plus minus 1, but it's a length. So we only care about the plus 1. So therefore, z is equal to 1. And then once you get z is equal to 1, x, which is equal to y, is equal to 2. So therefore, we basically got the answer. The volume is maximized if x is equal to 2, well, xyz is equal to 2 to 1. Okay, and then, and the maximum volume is f of 2 to 1. But what's f? F is xyz. That means 2 times 2 times 1, that's 4. All right, so that's the answer. Okay, so this is a method of Lagrange multiplier. So like I said, even if you have 3 variables, the idea is pretty much the same. You have 2 functions. The function you want to optimize, you want to maximize or minimize, and then the constraint, the function coming from the left-hand side of constraint. And what you have to set up is the equality of those 2 gradients. And then what you get is a system of 4 equations in the case of 3 variables, the last one being the constraint. And then what you want to do is to basically to play with the first three equations first, by sort of forgetting the constraint at the beginning. And then typically, you use the constraint at the very end of the calculation, just like this example. At the end, you get you use constraint to get the answer. And the same thing happens, by the way, in the previous program. Let's go back to the previous one. After all, once you get lambda, and by using 1, 2, and so on, you get x is equal to y. And then for the last calculation, for the last step, we use the constraint. 3 was the constraint for this case, the constraint function, constraint equation. Anyway, so this is the method of Lagrange multiplier. Okay, so this is pretty much the end of the video.